And we're live. Welcome everybody to the SAE meeting for March. I'm going to turn it over to Michael Bailing, who's going to kick us off.
Hey guys, welcome. So we have SAE Fellow Dr. Michael Wang from Argonne National Labs today to talk a little about the GREET model. We'll get in that to a little, but as everyone's trickling, we'll just do some of our standard SAE business for you. So just a primer, SAE Chicago, we have mainly members, some new members and some also prospective members. Hopefully you were able to forward the registration to some of your friends that were interested in this one. But SAE Chicago section is one of the largest in the nation, kind of right behind Detroit in number of members. We have over 1,000 professional members, as well as some student members in the local area colleges. So great for networking, job opportunities, learning about all kinds of different technology. And we're here to serve you guys. So anything that you guys want to learn about, always shoot us a note. Here's our board. So if you know anybody at your companies here, we also have all the major companies have.
Hey, Mike, you're not sharing. You're not sharing your screen.
Oh,
no,
I clicked it right before.
Oh, you're right.
There we
go.
Okay.
So back from the top, like I said, over 1,000 total members. So all kinds of stuff for everyone to do. And then these are some of the people that you can reach out to. So if you're interested in being on the board, being more involved, volunteering in the area, like I said, talking with the local university students, things like that, or presenting something happening at your business, feel free to reach out. We can always find some time to give you guys the floor. And then just make sure, again, you're following us on social. LinkedIn, we sure to make sure we post all of our stuff. We have one of our college students running our Twitter, so he's doing a great job at that. And then, like I said, every second Tuesday of the month is our Chicago board meeting. So if you want to be involved more with the board, just sit in, listen to what's going on, shoot one of us a note, and we'll be happy to set you up with the link for that. It's at 7:30 p.m. on the 8th, so coming up next week. So I think we got most of the people trickled in here. We want to give a introduction to Dr. Michael Wang here. So he's going to talk a little bit about GREET, which is the Greenhouse Gases, Regulated Emissions, and Energy Use and Technologies model. So it's been used by everyone across the world, industries and world on this one. So over 50,000 users globally. And we actually heard about it in the past year from our ClearFlame event and in the ethanol event, most recently in January. So very timely. And then Dr. Michael Wang's kind of done everything at Argonne. He's been there since 1993. He was kind of the founder of the GREET analytical model. So we're excited to hear from him on this one. And just last year, one of my favorite facts was he was named to the Reuters hot list of today's most influential climate scientists. So his resume more than speaks for himself, but I'll hand it over to Dr. Michael Wang now. And he can speak a little bit for the GREET model and what he's been doing at Argonne. So, Michael, if you want to give your screen share a try.
Okay, yeah. Let me know when you see one screen or two.
We're coming with one, just the presentation one,
Okay,
so it looks good.
That's great. Yeah, thank you very much, Michael, for the introduction. And team, thank you very much for the opportunity to speak to SAE Chicago section. So today I'm going to talk about the GREET life cycle analysis of vehicle technologies and fuels. So as many of us know, the US is a significant greenhouse emitting country. Last year, we emit about 6.5 billion tons of greenhouse gas emissions nationwide. So worldwide, we're number 2. China, of course, now is number 1 greenhouse gas emitter. Our transportation is about 1/3 of our total greenhouse gas emissions. In fact, the transportation sector is our #1 sector for US greenhouse gas emissions. And furthermore, many of us know the administration's announced a goal for United States to reach net zero carbon goals for electric sectors by 2035, and the entire economy carbon neutral goal by 2050. So from 6.5 gigatons to zero, it's going to be a tough challenge. Of course, transportation will have its fair share to meet that challenge. Michael mentioned our efforts to develop the grid model. In fact, we released the first grid version in 1995. Since then, we have annual updates and expansion. The model is available at grid website. So here, the flow chart and the bottom shows the so-called grid one model, or the fuel cycle model, or sometimes you hear the WTW modeling. So this is in grid one. On the other hand, we have grid two in the grid suite. Grid two is the so-called vehicle manufacturing cycle. And I'll touch on both grid one and grid two this evening. And I mentioned the transportation is #1 sector for US greenhouse gas emissions. If we take one more step about the transportation subsectors, here, this is the greenhouse gas share of the 4 subsectors: road transportation, about 72%. Our air transportation, 11%, rail is 2%, and marine is about 3%. So grid cover all the 4 transportation subsectors. This is a chart to summarize our grid user base. So as of now, we have over 50,000 registered users globally. And you see some major users with the company logos in the chart. And many OEMs are indeed intensive grid users. For example, these 3 OEMs and some international OEMs use grid. And as I mentioned, grid is available from our website. So here is the website. We have many publications besides the model posted at the website. And for what besides grid, let me turn my pointer. So besides grid, we have a few tools developed from grid, which I posted at the website too. Here is a summary of the grid suite. We have 2 modeling platforms, Excel and the .NET platform. And besides the grid version for US, we have international version for International Civil Aviation Organization. We have a China grid. As of now, we're developing Middle East and North Africa grid, and that version should be released sometime this year. The model has been used by different agencies for regulation development and for technology evaluation. For example, California Air Resources Board uses grid for its own low carbon fuel standard compliance. EPA uses grid for renewable fuel standard and for tailpipe greenhouse gas emission standards. And NHTSA has been used grid for CAFE standards development. As I mentioned, we developed a version for International Civil Aviation Organization for its lower carbon aviation fuel program. And most recently, the government of Canada used GREET for its own clean fuel standard development. This slide summarizes the output matrix in GREET. So we have 4 groups of matrix: energy used by different types, air pollutant, and these are the criteria air pollutant regulated by EPA. At greenhouse gases, we have the conventional greenhouse gases, CO2, CH4, and NO2, and we have some short-lived greenhouse gas emissions too. And finally, we have water consumption. This slide summarizes the so-called fuel production pathways included in GREET. So this is what covered in GREET Wang module. And we have petroleum-based fuels, natural gas-based fuels, and different hydrogen production pathways, electric systems, electricity generation from different fuels and power plant types. And we cover biofuels and renewable fuels extensively with different feedstocks and different conversion technologies. And in the last 2 years, we added the so-called electro fuels, which are the fuels produced from CO2 sources with renewable hydrogen from renewable power. This slide summarizes the powertrain technologies included in GREET for on-road transportation. So here we have gasoline engine technologies, diesel engine technologies, hybrid electric vehicles, plug-in hybrid electric vehicles, battery EVs, and fuel cell vehicles. And so I mentioned we have a GREET tool to cover vehicle manufacturing as well as the fuel production and use. So here is our approach for GREET tool simulations of a vehicle cycle, from material recovery to vehicle disposal. And over the last 15 years, we took the approach, as you see on this slide. Basically, we break the whole vehicle into the major vehicle component, such as body, powertrain, transmission, and so on. Then we get the material composition of each component. And then we look at the life cycle emission effect of different materials, and materials to parts, and parts to vehicles. So this is our GREET tool approach. And so far, we covered over 60 materials for vehicle productions. And we know we have still aluminum, plastic, rubber, and the different type of plastics, and different metals used in vehicle production. So these are the key materials we already covered in GREET 2 extensively. And one key issue for vehicle production LC is the use of virgin versus recycled materials can affect the vehicle cycle greenhouse gas emissions or environmental performance in general significantly. And in GREET 2, we have a very detailed battery LC module. So here is the coverage of the GREET 2 battery LC module. So we start with the critical materials for battery component production. And then for battery component, we have cathode, anode, battery, electrolyte, and battery management system. So step by step, again, we start with materials and always to the battery pack. And we have battery recycling included in grid 2. And in parallel, we have a very detailed battery recycling model. It's called Everbat. So that model gets into this area of the battery LCA significantly. So yeah, for any LCA model in general and grid in particular, data is the key. So LCAs are very data intensive. So we need a lot of data for material production, fuel production, and of course, vehicle operation. So here is the summary of the data sources we use for grid LCA. So for baseline technologies and systems, we rely on several government agencies' databases, such as those from Energy Information Administration, from EPA, and from US GS, and of course, some USDA databases for biofuels. And for the specific technologies we evaluate, such as crude recovery, electricity generation, we often rely on field operation data and simulations with models too, because for some new technologies, there is no operation data yet. So we do simulations such as the Aspen Plus model, the Argonne's autonomy model, EPA's MOVES model to generate the needed energy use and emissions for the activities in grid. And we have had a lot of collaborations with other organizations and with companies. So these are significant data sources for grid too. And so now I take you one step further. So what do we include in life cycle analysis? So this flowchart shows you the system boundary of LCA for crude and natural gas-based fuel cycles. So in this case, crude from oil field all the way to fuel combustion and vehicle. But for natural gas, is from natural gas field step by step all the way to either natural gas vehicle operations, or in the power plant case, we would stop here for power generation in natural gas-fired power plant. This is a chart to summarize the technologies and power generation pathways for US electric power sector. So as you see here on the left, we have different energy sources used for power generation, coal, natural gas, crude now become pretty minimum. Uranium for nuclear power plant, biomass, geothermal, hydro, solar, and wind. And then we have the process of getting those energy resources to a plant. They generate and transmission electricity to end use. So for end use, we have different end use sectors, as we all know, and we have hydrogen production from electricity as well. So besides the so-called fuel cycle in grid 1 from here to here, we have the plant cycle. So when we build our power plant, we know we need steel, cement, and other materials. So that's in the so-called plant cycle analysis. So with what we have for the US electric sector, now grid can generate the LCA result for power generation. So here, this bar chart shows you the greenhouse gas emissions in grams per kilowatt hour of electricity available at wall outlet, coal, oil, natural gas, geothermal, and other renewable power. So the renewable powers are capped below 100 grams per kilowatt hour versus coal and oil above 1,000 grams per kilowatt hour of electricity. And this map shows the US regional electricity carbon intensity, because as we all can imagine, different regions has different electricity generation mix from these plant types. So that reflect to the different electricity carbon intensities as you see here. And furthermore, if we look at Illinois versus US, and we see the Illinois electricity has somewhat lower carbon intensity than the US average electricity. That's because we have significantly large nuclear power share in our generation mix. As you can see, the nuclear power carbon intensity is very low, and we do include uranium enrichment, transportation, and those upstream stages. These charts summarize on recent publication we developed for Department of Energy in the so-called DOE ERE record. So here, we have the so-called current and future scenarios. Current is around 2020, future is around 2040 to 2050. As we all know, the technologies will advance over time, and our whole economy will go through decarbonization. And so those effects reflect from the current greenhouse gas emission performance to the future greenhouse gas emission performance. And then within each time frame, if you look at here, we have different powertrain systems, gasoline vehicle, diesel vehicle, hybrid electric vehicles, plug-in hybrid, battery electric vehicles with 300-mile electric range, fuel cell vehicles with conventional hydrogen production or renewable hydrogen production. So here, there are two key factors to determine the greenhouse gas emissions of these powertrain fuel options. One is the efficiency effect. From conventional technology to hybrid to electrification, efficiency plays a role for the downtrend from here to there. But also, if we look at a specific powertrain technology, the way to produce fuel plays an important role too. So here, hydrogen from different sources can have significant effect on the LCA result of greenhouse gas emissions. So here, let me explain the blue bars. The blue bars are the vehicle cycle result. The orange bars are the fuel cycle results. So basically, the emissions associated with the fuel production. This is the vehicle production. The gray bars are the vehicle operation-related emissions. So for electrical cars, we know there is no emissions from vehicle operation. So your blue bars are vehicle cycle result. If we take a step further of vehicle cycle result, let's see where are the emissions from for the vehicle cycle result. So here, body, this is a car itself for different powertrain systems, as you see here. Again, current and future. So body is blue, orange is chassis. So here, battery battery-related greenhouse gas emission contributions here. The fuel cell and hydrogen storage tank contribution is here. So now when we break down the vehicle cycle results to different vehicle component, we'll be able to see the effect of powertrain switch from here to there. Where do we see the switch in greenhouse gas emission burdens for a whole car? So that's we can generate from grid simulations. So yeah, those are some results for the US. In 2019, we worked with International Energy Agency to look at different powertrain system performance globally. So here I get the variation represent the performance in different global regions. And so here, these are the major powertrain systems we evaluate. So yes, there are variations among different global regions, but at the same time, we do see the downtrend if we advance the powertrain systems from standard or non-RCE technologies to hybrid, to plug-in hybrid, to BEV and fuel cell vehicles. But for BEV and fuel cell vehicles, how electricity and hydrogen produce are significant factors. So that's the result for passenger cars and SUVs. The US result for SUV, the global result was for passenger car. So now if we take a look at the heavy-duty truck LCA result for different powertrain systems and different heavy-duty truck classes, Class 6, Class 8 day cab, Class 8 sleeper cab truck. So in these three specific applications, the powertrain performance is very different. For Class 6, if we electrify, we see significant greenhouse gas reductions. But for Class 8, the benefit is not that significant relative to the diesel trucks. So that's a key factor we found out through our very detailed vehicle modeling with autonomy and our LCA modeling with grid. And this is some further result for hydrogen fuel cell. So as I mentioned, for hydrogen fuel cell, the way to produce hydrogen has significant effect. So this is the liquid hydrogen from natural gas, steam, methane reforming. This is what we see hydrogens produce now. But if we can move to the so-called green hydrogen production, in this case, the hydrogen from renewable power, we have significant reductions. Or if we have the so-called blue hydrogen, that's carbon capture and sequestration with a natural gas hydrogen plant, then we could move into this range. As some of you may know, there are some language in the bipartisan infrastructure law passed last summer. There are some specific hydrogen greenhouse gas standards proposed in the law. And at this moment, DOE is using grid to develop the standards for different hydrogen production pathways. This chart summarizes the biofuel production pathways in grid. So we have many biomass feedstocks on the left. We have many conversion technologies in the middle. and we result in different biofuels on the right. So these are various combinations of biofuel productions. What are highlighted in red in this chart are the significant biofuel productions as we see now in the US. For example, core ethanol, US produce close to 16 billion gallons a year now. Renewable natural gas from waste feedstocks, this has experienced significant growth in the last 5 years, both nationwide and in California. Biodiesel and renewable diesel has seen significant growth in the last several years, but biodiesel production has been stabilized near 2 billion gallons a year. So these are our significant biofuel supplies now in the US. This slide shows you the system boundary for biofuel LCA. And we start with fertilizer production. Our farming use a large amount of nitrogen fertilizer. So that's our first stage for biofuel LCA. Of course, farming is a significant activity. Biofuel production, biofuel use. Two key factors affect biofuel LCA results are first, land use change. As you see here, we include in grid. The other is the byproduct from a biofuel plant together with biofuels. For example, we produce animal feed in ethanol plant. We have soy meal from soybean together with biodiesel and renewable diesel. So the byproducts help the carbon intensity of biofuel to lower the carbon intensity of biofuel significantly. So while there are significant efforts here to address co-products in LCA, but in the last almost 14 years, the controversial issue has been on the land use change, and I'll touch on that later on. So here is a high-level summary of our biofuel results. So corn ethanol, we conclude with our most recent analysis, has a carbon intensity of 52 grams per megajoule versus our gasoline about 95 grams per megajoule. So core ethanol results in roughly about 45% reduction in greenhouse gas emissions on the life cycle basis. If we move to the so-called second generation biofuels, as we see the last three bars here, will have a much lower carbon intensity for ethanol. So some fact for Illinois, we are number 3 in the nation for biofuel production. So the number 1 state is Argonne, number 2 is Nebraska. So we are a significant biofuel producing state. As I mentioned, we conclude the core ethanol now achieve about 45% greenhouse gas reductions versus petroleum gasoline. So this is from a grid simulation. So now we want to take one step deeper. So where are the greenhouse gases for core ethanol? So here, as you see in this pie chart, ethanol plant account for about 43% of the total core ethanol greenhouse gases. The farming, these two together, land use change and the farming activity resulted emissions, these two together has about half of the core ethanol greenhouse gas emissions. So feedstock is a significant stage for our core ethanol carbon intensity. And if we look at Midwest state, we know the yield of corn is different in different states because the climate and soil conditions. And LCA results reflect that. So here are the major 9 corn producing states carbon intensity of corn fits into ethanol production. So you alluded to our recent study on corn ethanol. So last year we published a paper to document our examination of the US corn ethanol industry from 2005 all the way to 2019. 2005 is the first renewable fuel standard in place. Of course, in 2010, we have RFS2 in place. So our biofuel policies has significant effect on the biofuel volume to get us to now all the biofuels to get close to 20 billion gallons. And corn ethanol account up to 16 billion gallons. And we want to see whether we see some trend in carbon intensity of corn ethanol. So we use the USDA statistic data for farming and some industry survey for corn ethanol plant performance over the 15 years. And we conclude that corn ethanol CIs have decreased over the last 15 years by 23%. And this is from 2 sources. The corn ethanol plant CI reduction shows about 30%. So the plant itself reduced the carbon intensity by 30%. The corn farms has reduced carbon intensity by 15%. So these 2 together make the industry reduced its carbon intensity by 23%. That's why now we show corn ethanol in 2019 reduced greenhouse gas emissions roughly by 45% relative to petroleum gasoline. So land use change, I mentioned that we include land use change in LCA. And this has been a very controversial issue since 2008. So this chart summarizes the major studies for the US corn ethanol since 2008 up to 2 weeks ago. So overall, we see from the first study up to now, we see in general, the modeling result shows lower land use change resulting in greenhouse gas emissions. But the most recent study shows our land use change emissions are still significant, but still not as significant as the first study concluded. There are many factors to affect the result from different studies, including our own study. So I can get into the great details of what factors affect land use change emissions and or which way. But we'll see if we have time, we can get into some of the details. And many of us know where they are. Some transportation sectors is hard to electrify. The so-called hard to electrify subsectors, including aviation, long-haul trucks, and ocean-going vessels. So these are the sectors that will be hard to electrify. So liquid fuels are unique to continue to be the energy source for those sectors. So how are we going to decarbonize those subsectors? Biofuels or renewable fuels play an important role. So in the last 8 years, there have been significant efforts in the aviation sector to promote the so-called sustainable aviation fuels. So we expand GREAT to the aviation sector. So here are some great results we produced for different feedstocks, different conversion technologies to produce the sustainable aviation fuels. So again, just like road biofuel options, feedstock is important. If we have green as our feedstock, we have somewhat high carbon intensity versus if we switch the feedstock to waste sources. And of course, conversion efficiency play an important role to the carbon intensity of different SAF pathways. So this is just a sample what we've been doing in the aviation sector. So I show you some high-level methodology data sources as a result of LCA and GREAT. Of course, we still have some limitations in LCA for transportation. So let me summarize this way. So LCA has a long history for transportation. The first life cycle analysis for transportation, in fact, was in late 1960s and early 1970s for electric vehicles. Back there, that was what Department of Energy did. Then after that, there was significant effort in late 1980s and early 1990s for alternative fuel vehicles, life cycle analysis. So we have had a long history to use LCA in transportation. And I would conclude LCA is a major step to holistically evaluate sustainability of technology. So we can look at technologies holistically instead of back many years ago, we only look at the tailpipe emissions for vehicles. And now we look at the whole fuel cycle, the vehicle cycle, and vehicle operation. The LCA thinking has helped a change in corporations and consumer behaviors. So we know now corporations now have to disclose the so-called scope 1 to 3 emissions. So scope 1 to 3 emissions are supply chain emissions, or in different terms, LCA emissions. LCA-based regulations has helped promotion of sustainable technologies. We see that for biofuels from our retrospective analysis of US corn ethanol. And the process level details give us the insight for opportunities and challenges of technologies sustainability. But LCA results are still subject to variations and uncertainties. These system boundary depend on scope of LCA. You saw our system boundaries for petroleum fuels, natural gas fuels, electricity, and biofuels. And even we think our system boundary is comprehensive, there are still people ask for expand the system boundaries for LCA. And I mentioned the co-product effect results significantly, data availability and representation is a key issue for LCA result. When we analyze a technology, where and when the technology are in place for performance. So the where and when question is important because that's determine what type of data you use for LCA. Limitations of the LCA result. And we know sometimes we compare current versus the future. And sometimes we compare different technologies with different technology readiness levels or TRLs. And so this type of comparison sometimes can give people misguided information. So we need to be careful when we present LCA results to remind people if we compare whether we compare current versus the future or we compare mature technologies with the emerging technologies. So let me stop here to see if we have any questions.
Thanks, Michael. We did have a few in the chat. Iris, I don't know if you wanted to unmute to go on for this one, or we can do this one for you. She was wondering, just recently I found a quote from you actually about the Grivo collaboration. So I think it was a little bit on your slide on the premier aviation fuels and different feedstocks they're working with. I'm guessing that was the GEVO, G-E-V-O collaboration that you just announced in September?
No, actually, this is not. This is what we did for the International Civil Aviation Organization of the United Nations. So with different feedstocks and different conversion technologies. And we have more pathways example than what you see on this chart for Archaea. And for GEVO, what we did was the first part, core grain-based isobutanol, they isobutanol to jet fuel. So what we did is to look at their technology and where the opportunities. So where hydrogen is used, where natural gas is used, what are the opportunities to reduce hydrogen carbon intensity, where there are opportunities to reduce natural gas carbon intensity. So that's a study we did last year. We had a draft paper submitted to a journal. It's currently under review.
Okay, thank you. Anyone else have any other questions here?
Yeah, I had a question, Mike, and well, for those who didn't see the note that we put in the chat, if you do have any questions, please put them in the chat and then we will go ahead and moderate them out. Michael, when we had another group from the Iowa Corn Growers Association, they presented to us that the ethanol can actually be carbon neutral because when they grow the corn, it pulls CO2 out of the air. Did you factor in the CO2 that's absorbed in the growing process into the cradle to grave farm gate activities?
Yeah, we did. So here, as you can see, there is no vehicle operation greenhouse gas emissions from this part for ethanol. That's because the carbon in ethanol is the carbon from the air, the so-called carbon neutrality approach. So that's built in, and the corn ethanol plant fermentation process produce significant amount of CO2 emissions, as we all know, because we know the beer distillation produce CO2 just like ethanol plant. And we do not take into account the fermentation CO2 in this part, because that CO2 is from the CO2 from the air during the corn plant growth. So that's carbon neutrality. So even with that, we still see a significant greenhouse gas emissions. Why? Because we use larger amount of natural gas in ethanol plants to to generate steam. So that's direct CO2. But if we use renewable natural gas instead of fossil natural gas, we can remove large amount of the ethanol plant CO2. The cornfield emissions, there are some data which shows that soil organic carbon content has increased over the last 30 years, 40 years in corn farms. So there are long-term soil organic carbon data showing the increased soil carbon content. That's in a way, it's carbon sequestration from the air to plant roots, and they add up in soil. That soil carbon sequestration is not included in our analysis, because we're still doing a lot of analysis to see whether we have reliable data on SOC. Plus, EPA and California do not take into account SOC changes. So because of that, we do not take that. If we take those measures into this calculation, as we see here, then we could get into a carbon neutral situation.
Okay, very good. Well, I've just opened the mic to Mr. Phil Fair. Phil, go ahead and ask your question.
Okay, first, thanks, Dr. Wang and Argonne for the presentation. About midway through on your presentation, I noticed a couple of slides that show different vehicle segments and greenhouse gas emissions. Notice that the big trucks like Class 8 and up did not have heavy emissions. And I was just wondering if that fact is somehow related to all the attention that auto driving technologies is given to that segment of vehicles.
Well, these are your long haul Class 8 trucks, and we know under the freeway drive, diesel trucks are somewhat efficient. On the other hand, battery EVs, battery electric trucks, and fuel cell trucks, under those operation conditions, their relative efficiencies is better than your diesel trucks, but not by a huge margin. So that's reflected here. And whether automation will help these two technologies over diesel trucks, I do not know. I think maybe the technologies could help all three together. But for all of us knowing how those long-haul trucks operate, especially when you carry a large battery packed with the battery electric trucks, that penalizes your efficiency.
Yeah, just from my point of view, I'm from Navistar, so in the heavy truck industry. So not talking about any technology related, but Phil, maybe some of that could happen with lowering the speeds. So right now, truckers are driving 70, 75 miles per hour sometimes, and obviously aerodynamics comes into play there. And so the slower you can bump that down, the more fuel efficient trucks are, and even if it's not fuel, if it's battery, battery efficient they are as well. So you'll find big gains there, but that's kind of going to be across the board just because of aerodynamics. So hopefully that helps.
Yeah, I agree. The aerodynamics definitely help trucks when we slow down a little bit from 65 or 70 miles an hour to some lower speed, maybe around 50 miles, 55 miles an hour.
Dan had one in the chat, if you want to unmute and ask it.
Yeah, Dr. Wang, I want to hear your response on the latest publication in National Academy of Science from a study by University of Wisconsin on corn ethanol, claiming it actually has a greenhouse gas 20% higher than gasoline.
Yeah, so So that paper is the last one of this bar. So as you see, our land use change shows about 7 grams. California shows about 20 grams. EPA's 2010 result shows about 28 grams. This is the land use change emissions only. So if we add what they have here, you remember I said our conclusion is the core ethanol now is about 45 or 52 grams, including our 7 grams. So 52 grams and another 744, so that's your 37, right? 37 grams to 52. Let's get ourselves pretty close to the 95 grams of petroleum gasoline. So, so we're say even with large look numbers, they conclude break even, not increase. But if they add their number from EPA's number, then their overall LCA result will go above 95 grams.
Okay, thank you very much. I think this reflects you understand the assumptions embedded in that study as well.
Mm-hmm.
So I appreciate your direct response to that question.
And I have one more question. There's some organizations saying that renewable natural gas that would, if you capture methane, that would otherwise leak into the atmosphere and burn that in transportation applications. It would again be actually climate friendly in that methane is a worse greenhouse gas than CO2, and you're actually, reducing the impact on the climate if you could do that. And that by burning the renewable natural gas, we can actually improve the situation. Your thoughts on that, Dr. Michael Wang?
Yes, that's a good question. So, as you saw in one of the slides, we have renewable natural gas included in the grid. So, by produce renewable natural gas from either municipal solid waste or animal waste, we avoid methane emissions from landfills. We avoid methane emissions from animal farms, from animal waste. Those are we call counterfactual scenario emissions. So now we take those feedstocks for RNG, we avoided the counterfactual scenario emissions. Because the avoidance of counterfactual scenario emissions for each megajoule of RNG produced, we in some cases conclude from grid RNG can result in a negative greenhouse gas intensity of negative up to 300 grams per megajoule negative versus 95 grams positive per megajoule for gasoline. So now if you subtract those two, suddenly you have a credit close to 400 grams per megajoule by switch from gasoline to RNG. In California under LCFS, each ton of CO2 is worth about $200 per ton. So now with 400 grams per megajoule, if you sell a gallon of your gasoline equivalent gallon of RNG in California market, that huge credit worth about $5 to $7 per gallon. So you can give your RNG for free to your customers, just claim that carbon credit still will come out with a big win. So that's how significant the credit is. And that's the driver for the significant growth in RNG in the last 5 years.
No, that was some of the stuff that ethanol guys had mentioned. So thanks for putting that into perspective because they just touched on it. So very helpful. John, any other questions you saw or anyone message you?
I don't see any other questions, so I think we're right on time here. So we thank you, Dr. Michael Wang, for coming on. We thank everybody who joined tonight. This will be available on our YouTube channel should you want to go back and watch it again. So thank you, everybody, for coming. Mike, any closing comments?
Yeah, so just that Dannon question and some of the stuff that just recently came out, I included in one of our publications as well. A little further reading on what we were talking about, the land use change on all of that stuff. So some of those are in the chat if you're interested in them. And that GEVO partnership as well. I'll put a link in the chat for that. As you can see, our speaker here got a little press in his name for that one. And then as a final, just fun end of the night here, you have two further watching options. I'm a University of Wisconsin grad, so I'm pulling for my number 10 Wisconsin Badgers. But if you're not a college basketball fan, feel free to tune in the State of the Union. I'm sure Joe Biden will talk a lot about all of this net zero carbon capture, energy, all kinds of stuff like that. Maybe Dr. Michael Wang even had some notes that he passed on to give him for his speech, so he was all prepared. So enjoy your night, guys. And thanks again to Dr. Michael Wang. We really, really appreciate it. Love the work you're doing at Argonne. And thanks for sharing the GREET model with us.
Yeah, Michael, thank you again for the opportunity.
Okay.
Great. Thank you.
Good night, everyone.
Right.
Okay, good night.